Okay, everyone. So in last class, we talked about the hypothesis testing applied to one sample. We want to compare this sample's mean to a population's mean, and we have no information about the population's standard deviation. So I introduced you guys the t-test, how to calculate the t-score, how to use the t-table, and then how to make the decision. So first, I want to give you guys a recap by going through the practice, the Moon illusion practice I gave you guys in the first week. So for this Moon illusion practice, the prompt or the question we want to address is, so here we have collected 10 people, and we ask these 10 people to estimate the diameter of a horizon mole after they were given a zenith mole, the standard mole. And we kind of measured the diameters of their estimated or perceived horizon mole, and then kind of find the ratio between the horizon mole and the zenith mole. So if this ratio is larger than 1, we can say that people tend to perceive the horizon mole is larger than the zenith mole. And if this ratio equals to 1, so we can conclude that people perceive that the horizon mole is as large as the zenith mole. Okay, so this is kind of the basic setup or the context of this question. So here we have these 10 people, our samples, their ratios. So these 10 numbers or 10 values are the 10 data points we have. And I have calculated the mean for these 10 scores for you guys, which is 1.463. And the standard deviation for these 10 data points is 0.341. Okay, so some of you may ask me, then what is the mean for the population, right? What is the mean we want to compare our sample with? The little trick here is, well, think about it. We want to compare whether these 10 ratios are significantly than the standard ratio. So what is the standard ratio? That is 1, right? So we want to see whether people tend to perceive this horizon mole larger than the zenith mole. Let's say if these two moles have the same diameters, the ratio should be 1. So essentially, we are comparing these 10 data points with the population, and this population's mean is 1, and we have no idea about this population's standard deviation. Okay, so this is kind of the data or the statistics for this question. We have a sample size of 10, the sample mean is 1.463, and the standard deviation is 0.341, and the population's mean is 1. And this statistic, this data, is pretty enough for us to address this question. Do people tend to perceive this horizon mole larger than this zenith mole? Okay, so we're gonna go through several steps as we did before. The first one is, of course, to set up the null hypothesis. Okay, so the null hypothesis is we suppose that our participants are perceiving exactly same mole size between the horizon mole and zenith mole, right? The ratio should be 1. And this alternative hypothesis is that this ratio is not equal to 1. And second step, pretty much like what we did for the z-score. So we're going to assume this null hypothesis is true, right? People's estimated ratio equals to 1. And this difference between our observed sample mean with this standard ratio mean, it's just kind of due to chance, due to observation bias. So we assume that this null hypothesis is true. And next step, we're going to build a sampling distribution of means. Okay, and for this time, we do not have the population's standard deviation. Instead, we can use our sample's standard deviation to estimate the standard deviation of this sampling distribution of the mean. And for this statistic, we call it a standard error. We have talked about this concept in last class. Okay, so again, for this sampling distribution of the means, the standard deviation for this sampling distribution, we call it a standard error. So we want to learn more about this sampling distribution of the means, such as its mean and its standard error. So what is a mean? According to the central limit theorem, the mean for this sampling distribution of means equals to the original population's mean, and in our case is 1. Okay? And we are gonna also calculate this standard error, that is the standard deviation of this sampling distribution of the means. We're going to use our samples SD to estimate this standard error. Okay, so we're going to use S, our samples SD, over the positive square root of our sample size. Okay, and we plug in the numbers. Here we plug in our samples SD 0.341 and divided by the square root of 10. 10 is our sample size. Okay. So again, we have no information about our populations, the population's standard deviation. We don't have the information about the sigma. So we are using our sample's standard deviation to estimate this standard error. So in this case, we are not using the z-score anymore because it's not accurate, it's not correct. We're going to use a new distribution or table to correct this biased estimate. Okay, so after we have this kind of statistic information about our sampling distribution of the means, then we're gonna kind of look at where does our observed sample mean stand in this sampling distribution of means. Okay? We're gonna calculate the t-score for our observed sample mean. Okay, so these first two lines I just list the basic information of our sample and the sampling distribution. Okay. So the third step is to calculate the t-score of our observed sample mean. Okay. Again, we are using sample's standard deviation to estimate the standard error. With the same with the z-score, we're gonna subtract the mean of our sampling distribution, which is our population's mean, which is 1 in our case, from our observed sample mean. Okay, and then divided by the standard error. Okay. And then we have calculated this part in last slide, and then we plug in all the numbers. So 1.463 is our sample's mean, and minus 1 is our the mean for this sample distribution, which also equals to a population's mean, and divided by this standard error, and give us the answer 4.29. So 4.29, that is our obtained t-value given this sample. Okay, so right now we have our obtained t-value. The next step is we want to check the t-table to find out the critical t-value given our sample, which is the sample size is 10, and given the setup of our research question, which is a two-tailed test. Okay, and we also set the significant value as 0.05. Okay, so I'm gonna switch my screen to the t-table, and then we are gonna altogether find out the critical t-value for this setup. Okay, so this is the t-table. I uploaded this table on Canvas in the file function. So you can access to this table through the file function, or you can just find this table in the module function. I linked our module with the file with this t-table. So let's find out the critical t-value for our sample size. So our sample size is 10. We have 10 participants in our sample. And the first thing we want to do here is to find out the degree of freedom, which is 10 minus 1 give us 9. Okay, so let's see. I'm gonna draw this kind of for you guys. Okay, so we are looking at this line here with a degree of freedom of 9. Okay. And like I said earlier, the t-table is a little bit different from the z-table. The t-table gives us the critical cutoff p-value, the probability value. And then we're gonna try to find out the critical t-value given a particular p-value, okay? We are using a two-tailed test with a significant level of 0.05. So here is the column we are looking at, okay? So two-tailed test and with a significant level of 0.5, okay? And we want to look at this intersection here. So the critical t-value we identified given a sample size of 10 is 2.262. So what does this critical t-value mean? And how do we compare it with the obtained t-value? Let me kind of draw you guys this distribution. So here I'm drawing a sampling distribution of the mean, okay? And this sampling distribution has a mean of 1, which equals to the population's mean, okay? And we also checked the critical t-value given a sample size of 10 and a significant level of 0.05 and a two-tails test, right? So we have this critical t-value here, 2.262, okay? So what does this 2.262 mean? Okay, so it means that if we kind of draw such a normal distribution of this sampling distribution, so 95% of the values will be accumulated within the range. And what is the range? That is 2.262 units of standard error above the mean of 1. Okay, so again, the standard error means the standard deviation of this sampling distribution. Okay, and the lower limit of this range is 2.262 units of standard error below this mean. Okay, so let's take a look of our obtained t-value, which is 4.29. So it's way far away from this critical t-value. So we can see that holding a sample size of 10 and we are doing a two-tailed test with a significance level of 5% or 0.05. The likelihood of obtaining such a t-value as large as 4.29 is very, very unlikely. So we are gonna kind of question the assumption we just made. We're gonna reject the assumption. So this brings me to my last step here, which is, let's see, the obtained t-value is 4.29 larger than this critical t-value we found in the table. So we're gonna reject the null hypothesis and conclude that the true mean ratio is not equal to 1 to the population. And this further leads to the conclusion that mole illusion does exist, and people tend to view the horizon mole larger, significantly larger than the Danish mole. Okay, so by talking about the significant, by inserting this word in our conclusion, we mean that this observed difference between this sample mean and the population is a true difference. It's not coming out of observation bias or chance. It's a true difference. Okay, so from now on we are gonna kind of try to insert this significantly word into our conclusion, saying that people view horizon move significantly larger than the densmol. And this significantly word means that there is a true difference existing between the sample and the population.